Is string theory dead? For years, a seemingly insurmountable problem, dubbed the Swampland, seemed to have condemned it, relegated it to the realm of pure mathematics, far from the reality of our universe. But today, a new, audacious idea might have not only saved it, but also solved some of the greatest mysteries of cosmology. What if I told you that, in a sense, strings are already an observed and tested reality in our particle accelerators? If these mysteries of the universe fascinate you, subscribe to the channel so you don't miss the next videos. Make yourselves comfortable, because we are about to explore the possible rebirth of the most ambitious theory in physics. The idea behind string theory is disarmingly simple. Everything that exists, from particles to light, is not a point, but a tiny vibrating string. An elegant, almost poetic idea. The problem is that, for decades, the mathematics did not cooperate. When physicists tried to build a universe based on these strings, they were faced with an infinite number of possible theories. The vast majority of these theories, which form what is called the string theory landscape, while mathematically consistent, do not resemble our universe at all. Furthermore, the few theories that seem compatible with our cosmological observations are found in what physicists have called the Swampland. The Swampland is the set of all those theories that seem to work at low energies, but which inevitably break down at higher energies, proving to be incomplete and incapable of being a true theory of everything. For a decade, this has been a severe blow. Either the theory was consistent and unified everything, or it agreed with observations. It didn't seem to be able to do both. Here enters a revolutionary proposal advanced by physicist Eduardo Guendelman. What if one of the pillars of the theory was wrong? Until now, it has always been hypothesized that the tension of a string or its rigidity was a fundamental constant of nature, equal for all strings, in every time and place. Guendelman, in his article published in the European Physical Journal, proposed to transform tension into a dynamic variable, a value that can change depending on the energy. This apparently simple idea has profound consequences. It would allow the universe to exist in a low-energy state compatible with our observations, and then transition to a high-energy state, that of the universe's origins, where forces unify and the theory works perfectly. As if the theory could finally work at both low and high energies, aspiring to be a true theory of everything. This dynamic tension could also provide a theoretical basis for cosmic inflation, the explosive expansion that occurred in the very first moments of the universe's life. The idea is that, in the very first moments of the universe, the tension of the strings was immensely higher than today, consequently leading to a gigantic Planck scale. This extended Planck scale would have created the ideal physical context for the onset and sustainment of inflation, which would otherwise be extremely improbable with the current string tension. But it doesn't end here. The new variable tension theory could even explain dark energy, and I'll explain how. Imagine dark energy as a ball slowly rolling on an almost horizontal plane. This slow descent generates the constant push that accelerates the universe. In standard string theory, this plane is always too steep. The ball would roll away immediately without producing the desired effect. The new theory, however, introduces a tension field that acts as a cosmic leveler. Where this field is strong, it can flatten the dark energy potential, creating the almost horizontal plane we need. In summary, we have seen how string theory with dynamic tension can explain a series of phenomena that the standard versions struggle to justify, relegating them to the swampland. It is important to emphasize that this is, for now, a theoretical hypothesis, a bold proposal that still needs to be verified. But it opens up an incredibly promising path. But beyond these new and speculative frontiers, did you know that strings are not just a hypothesis for a theory of everything? They are a well-tested reality in another field of physics, quantum chromodynamics. the theory that describes the strong nuclear interaction. This theory describes the behavior of quarks, the fundamental building blocks of protons and neutrons. Quarks have a bizarre property. They are confined. We have never, ever observed a free quark in nature. The reason is that the force that binds them, unlike gravity or electromagnetism, increases with distance. It's as if they are tied by a very powerful elastic band. Physicists describe this bond precisely as a string, or more technically, a flux tube of energy that connects two quarks. The more you try to pull the quarks apart, the more energy accumulates in this string. At some point, if you pull too hard, the accumulated energy becomes so great that it is more convenient for the string to break. But when it breaks, two new particles are born from that pure energy, a new quark and an antiquark, which bind to the original two. This phenomenon, called hadronization, is not a hypothesis. It is something that is constantly observed in particle accelerators like CERN's LHC. Physical models that treat these interactions as relativistic strings are able to make incredibly accurate predictions about the results of experiments. What's even more astonishing is that as early as the 1970s, physicists realized that by trying to make this string theory of chromodynamics compatible with quantum mechanics, the mathematics predicted in a completely natural way the existence of another particle, a massless particle with spin equal to 2, which are exactly the properties that the graviton, the hypothetical mediating particle of the gravitational force predicted by string theory, should have. It was this discovery that caused interest in string theory to explode as a possible theory of quantum gravity and, finally, as a theory of everything. The connection between chromodynamics and the graviton remains one of the most solid pillars in favor of the development of string theory. In conclusion, so, what is the future of string theory? On the one hand, we have new and radical ideas like dynamic tension that attempt to solve cosmological problems and make the theory agree with our observed universe. On the other hand, we have the solid experimental reality of quantum chromodynamics, which shows us how the concepts of string and stored energy within it are not pure fantasy, but successfully describe the subatomic world. String theory as a theory of everything remains speculative, however, and still lacks experimental verification. However, these developments show us that it is a field of research more alive than ever, capable of generating powerful ideas and creating unexpected bridges between different areas of physics. It is not dead science, but an intellectual adventure that, for better or worse, continues to push the boundaries of our knowledge. And you, what do you think? Is string theory the right path or a very elegant dead end? Tell me your thoughts in the comments, and don't forget to leave a like if you enjoyed the video. Alla prossima!